Okay, kids, ready to do our last chapter 4 method, and it is an old method, our MVP method, variation of parameters just on higher order. So what's nice is that assuming the fundamental set of solutions, which remember, we take the complementary, the Wronskian not equal to 0 when we practiced at the beginning of this chapter, taking Wronskians with higher order, but only 3 by 3s. That I would not ask you to do higher than a 3 by 3 by hand. That unlike the method of unit of the undetermined coefficients, we can only use that method when our non-homogeneous piece of the differential equation is sines and cosines, or e to those, or polynomials, or any combination thereof. But what about when you don't have that? Excuse me. If you don't have that, the method of variation of parameters always works, but it involves integration, which is why I would prefer not to use it. As a matter of fact, sometimes the integration is undoable, and we have to actually leave our final answer in terms of an integral. So if you want to see if you want to remember where the formula comes from, right? I did the proof for the second order back there in 3.7. You can go refresh your memory if you like, because I'm just really going to give you the formula here. We're not going to go through the proof. So let's do this example. Again, with it equal to e to the x, I don't really have to use method of variation of parameters, but I want to practice using this, right? I could just easily use the method of undetermined coefficients. I'm going to give you the complementary solution or the homogeneous solution, right? So I factored the characteristic equation, and I got real roots of 1, 2, and 3, which is where those came from. So we assume a particular solution, this time not dependent upon, right, like the method of undetermined coefficients. The form of the non-homogeneous piece was what determined our particular. But for the method of variation of parameters, how we decide upon our particular is we just replace all these coefficients with an unknown functions, v1, v2, and v3, and we're going to try to set up a system where we solve for v1, v2, and v3. But of course, since it's third order, we need to differentiate 3 times, right? So this is function 1, this is function, right? Unknown function 2, unknown function 3, and this is our y1, y2, and y3. And we need to differentiate each one of those 3 times. When we were solving a 2 by 2 system, we needed to make 1 claim. Here we have to make 2 claims. Again, when we differentiate, we're going to get a bunch of product rules. We're going to get some things to cancel out. We're going to get some things to combine. We are also going to have one piece of the derivatives where we have our y1, y2, and y3 all with derivatives of their v's. We want to claim that equation is equal to 0, as well as the pieces of the first derivatives of our unknown v functions with our known y functions, their derivatives. Both of those equations we're going to claim are equal to 0. And there we're going to make an equation where we have our 2 claim statements right here. And then this is our y sub p after taking the second derivative. Okay, we're going to say that part is equal to the non-homogeneous piece. And again, if you want to see where that comes from, I do all the algebra of this on the 2 by 2. Right? This is the non-homogeneous part. So for us, that's e to the x. So we are going to solve this system using Cramer's rule. Good old Abel, right? He did, right? He was that way to show us how to find the, right, the Wronskian. We could use Abel that way. Also, Cramer's rule for solving a system is also the method of determinants, where the coefficients that we're after, 3 equations with these 3 red unknowns, solving for the 3 red unknowns, Each one is a ratio of determinants. All three determinants have the same denominator. I call that D. Each one has a different numerator. So I just need to tell you how to find, not how to find a 3 by 3 determinant. You know how to do that, but which determinants are each one of these. So here you go. You ready? Bam! Oh, wait, I forgot. I don't actually want to solve for v prime. I want v, which is where the integral comes in. So, bam, that's what I meant. Notice that I have 4 exact same determinants. They're not going to all be the same, though. So the D determinant, this is the determinant that goes in the denominator of all 3 ratios. This is just y1 and its derivatives, y2 and its derivatives, y3 and its derivatives. So I do my work. I trust you. I don't need to go through this, but I'm going to call that determinant W. The next determinant and the numerator of the first ratio is the exact same determinant except the X column, if you will. The first column is replaced with 0, 0, 1. Now this can be expanded to any higher order. And I would be replacing, let's say I had a 4 by 4 system. I would be replacing the X column with 0, 0, 0, 1. Okay. And I'm going to calculate that determinant. The second numerator comes from replacing the Y column with 0, 0, 1, and I bet you're not going to be surprised to know that the last numerator is found by replacing the third column with 0, 0, 1. So for the method of variation of parameters, I'm going to call the D matrix, that one that goes in the denominator of all 3, I'm going to call that the Wronskian, because that's what it is, the Wronskian. Each one of these is really a Wronskian. That's my first Wronskian, my second Wronskian, and my third Wronskian. When you are solving a 3 by 3 system outside of the method of parameters, this is the same way you do it. You replace the X column, the Y column, the Z column, but you replace it with the column of the answers, of which 0 and 0 are the equal, right? The first claim is equal to 0, the second claim is equal to 0, and the third equation is equal to the non-homogeneous part. So for us, that would be e to the x. Again, there is a proof of why you can replace the non-homogeneous part in the method of variation of parameters with a 1. And it does, of course, make our math a little easier. So I did this and I got 2e to the 6x. This one was e to the 5x. So you might want to pause the video or on your own time, see if you can get these same answers. Where's my last one? E to the 3x. Okay, so I need all 4 of those Wronskians to use in the variation of parameters formula for higher order. No negatives. Remember, for the 2 by 2, I always had a negative in front. So notice that, this one uses u's. I like to use v's for the variation of parameters. So g of t is your non-homogeneous piece of the differential equation. This is the D determinant, that very first one that is actually your Wronskian. And then this is your Wronskian when you replace the X column with 0, 0, 1, the Y column with 0, 0, 1, and for us the Z, and that's the highest. I know this, I just captured this from a screenshot, right? Comma, dot, 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 because as I said, this can be expanded to however many you want. We are only going to do third order for variation of parameters and BP method. So for us, this would be V sub 3 And this would be the W sub 3. Okay? So let's go ahead and work our magic here. So V prime of 1, V of 1 is the integral of 2e to the 6x, and I'm going to osmosis the 2 in that denominator out here, g of t, and then my first Wronskian, my first replacing Wronskian, which was, what did I say that was? E to the 5x. Right, so that's going to be e to the 6x over e to the 6x, which is just going to be 1 dx, which is 1/2 x. V2 is equal to 1/2 times the integral of e to the x over e to the 6x. And my second Wronskian was negative 2e to the 4x, right? So I'm going to put the negative 2 out here. So I get negative 1. What is this? This is e to the 5x over e to the 6x. And this is e to the is that e to the negative x or e to the, yeah. Divided by negative 1, so that's going to cancel, make this negative 1 positive. V sub 3, 1/2 e to the x, e to the 6x, and my third Wronskian, which was e to the 3x. Over negative 2. So what does that make my particular solution? So my particular solution is going to be 1/2 x times e to the x, and e to the negative x times e to the 2x, and negative 1/4 e to the negative 2x times e to the 3x. Clean that up. These are both e to the x's. And remember, when I combine everything with my, complementary, right, I already had an e to the x. So I don't need to write those one down, right? Because that's just a constant times e to the x, and that's already taken care of there. I have C2 e to the 2x, C3 e to the 3x. So the only thing I needed to add on was the 1/2 x times e to the x. What the heck? That's supposed to be an e to the x. Okay. Remember, the e to the x terms that I had all got wrapped up into here. Let's do one more. So again, if you want to pause the video and check out, see if you can match my answer. I didn't type this run S, I just captured a bunch of screenshots for this. Here's my complementary, which of course I normally call the homogeneous, right? I got my characteristic equation and found the roots, -3, -1, and 6. Made my complementary equation the same as my homogeneous, but with functions in front of each one of those instead of constants. Got out my formula. Again, this where I got this from. They like to use U, I like to use V. You do what you want. Bam, there's my Wronskian work. Remember, this is the actual Wronskian is going to become the denominators of all three ratios. This is the numerator when you replace the x, the numerator when you replace the y, and the numerator when you replace the z column. And I've given you all the answers there. So integrating the first one, here was your D. This was your non-homogeneous piece. And this was the first Wronskian when you replace the x column. Okay, so did some simplification, got a nice, right? Some nice e to this. Divided this by 3, divided that by 2. There's my second one. You can see it has the same Wronskian in the denominator. And my third. And remember, each one of these is not my actual answer. I need to multiply each one of those times y1, y2, and y3. So there's y1, y2, and y3. Did some math, simplified. Got some nice situations here. Combined it into my one solution with my 3 constants. This time there was no overlap, so I actually had 1, 2, 3, all 3 terms from my particular. Woot woot, right? So this one, unlike the method of undetermined coefficients, at least with the MVP, I am doing some calculus, right? I am doing some actual integration. And I am going to test you on ones that you can do. Notice that with my G of t being right there, I could have used the method of undetermined coefficients on that. So again, just like I did with in chapter 3, I will prompt you, use the MVP or use the MUC. Okay. All right, I will see you in our next live session.